Hello, my friend, and welcome to Orbital Dreams. You are here tonight because the universe allowed something incredibly rare to happen. Somehow there is air to breathe. There is water. There is warmth from the sun. There is a world beneath you and stars above you, and none of it had to exist this way. The universe could have been empty, dark, and silent, and yet here you are, breathing, listening, and resting inside a cosmos that somehow became possible for life. So tonight, we'll gently explore why the universe seems so strangely suited for us to exist at all. And as we move through these quiet cosmic questions, you can let your thoughts slow down, let the stress of the day soften, and allow this vast universe to make your worries feel just a little smaller. Settle in, my friend. Let the day fade away, and let's begin with the strange luck of being here. Chapter 1. The strange luck of being here. The question of why the universe allows life at all is one of the most fundamental mysteries in science, because hidden inside it is the astonishing possibility that existence depends on a chain of conditions so delicate that changing even one part could have left the cosmos dark, simple, and silent. When we look around from the surface of Earth, life can feel ordinary. The sky appears every morning. The ground holds steady beneath our feet. Air fills our lungs without needing our permission. Water gathers in rivers, oceans, clouds, and cells. Stars shine at night with such quiet regularity that it is easy to forget how strange their existence really is. We are born into a world where atoms hold together, chemistry works, gravity gathers matter, and sunlight arrives from a stable star. Because all of this surrounds us from the beginning, it can seem natural, almost inevitable, but science has shown us something much more surprising. The universe did not have to be this way. There are many possible ways to imagine a universe that would be physically real, but lifeless. A universe could expand so quickly that matter never clumps into galaxies. It could collapse too soon, before stars have time to form. It could contain no stable atoms, no long-lived stars, no heavy elements, no planets with surfaces, no liquid water, and no chemistry complex enough to build cells. It could be filled with particles that rush apart forever, or crushed into blackness almost as soon as it begins. It could be beautiful in its own way, but it would never ask questions about itself. Our universe somehow avoided all of those dead ends. That does not mean the universe is comfortable or safe. Most of it is hostile to life. Space is cold, nearly empty, and flooded with radiation. Stars can destroy the worlds around them. Black holes, supernovae, and high-energy events remind us that the cosmos is not gentle in any human sense. Even on Earth, life survives only within a narrow range of temperature, pressure, chemistry, and energy. So when we say the universe is unusually suitable for life, we do not mean that every corner of it is welcoming. We mean something more subtle and more profound. We mean that the basic structure of reality allows life to be possible anywhere at all. This is the heart of the mystery. Life depends on layers of order. First, there must be particles that can exist long enough to become atoms. Then atoms must be able to combine into molecules. Molecules must be able to form structures that store information, move energy, and respond to their surroundings. Stars must exist to make many of the elements that living worlds need. Planets must form from the material left behind. Some planets must have stable conditions long enough for chemistry to become biology. And somewhere in that long chain, matter must become organized enough to wake up, look around, and wonder why the chain was possible in the first place. Nothing in that chain is simple. Hydrogen, the lightest and most common element, formed early in cosmic history, along with helium and a small amount of lithium. But hydrogen alone is not enough for life as we know it. To build rocky planets, oceans, atmospheres, and living bodies, the universe needed heavier elements such as carbon, oxygen, nitrogen, phosphorus, sulfur, silicon, iron, and many others. These elements were not present in large amounts at the beginning. They had to be forged later inside stars, scattered through space by stellar winds, supernova explosions, and the violent merging of dense stellar remnants, then gathered again into new generations of stars and planets. This means that life is not merely sitting inside the universe. Life is made from the history of the universe. Your body is not separate from cosmic evolution. The atoms in your blood, bones, skin, and breath were shaped by events that happened long before Earth existed. The calcium in bone, the iron in blood, the carbon in cells, and the oxygen you breathe are connected to the lives and deaths of stars. A living body is not just matter arranged on a planet. It is ancient cosmic material, temporarily organized into awareness. But even the creation of elements is only one part of the story. The universe also needs stable rules. If the strength of gravity were very different, cosmic structure would change. If electromagnetism behaved differently, atoms and molecules might not have the same stability. If the nuclear forces inside atoms were changed, stars might burn in a very different way, or certain elements might not form in useful amounts. If the expansion of the universe had followed a very different path, matter might never have collected into galaxies, or the universe might not have lasted long enough for complexity to grow. This is where the feeling of strangeness begins to deepen. The universe is not just full of ingredients. It is full of relationships between ingredients. Gravity pulls matter together, but expansion carries distant galaxies apart. Stars compress gas inward, while nuclear energy pushes outward and keeps them shining. Electrons are held around atomic nuclei, making chemistry possible. Quantum rules give atoms their structure. Thermodynamics gives time a direction and allows energy to flow from useful forms into less organized forms. Life does not require one lucky fact. It requires a whole architecture of compatible facts. And yet here we are. The most careful way to say this is not that the universe was made for life. Science cannot honestly jump to that conclusion. The universe may be the way it is for reasons we do not yet understand. Some features may be necessary consequences of deeper laws. Some may be accidents. Some may only look surprising because observers can appear only in universes where observation is possible. This idea is called the Anthropic principle, and we will return to it later. For now, it is enough to notice that there is a real puzzle here, even if we do not yet know what kind of answer it will have. The puzzle becomes clearer when we remember how small life is compared with the whole cosmos. Earth is one planet around one star in one galaxy among vast numbers of galaxies. The part of the universe we can observe is immense beyond normal human intuition. And within that immensity, ordinary matter, the kind that makes stars, planets, oceans, and bodies, is only a small fraction of the total cosmic contents. Much of the universe appears to consist of dark matter and dark energy, whose full nature remains unknown. So life is not standing at the center of reality. It is a fragile pattern made from a small portion of what exists, in a universe mostly built from things we still do not fully understand. That makes the question even more powerful. Why should such a universe allow minds at all? Why should a cosmos dominated by darkness, distance, and unknown forms of energy also contain the possibility of warmth, memory, thought, and care? Why should the laws that govern galaxies also allow a human hand, a breath, a heartbeat, a sleeping animal, a forest, a coral reef, or a person listening quietly at the end of the day? These questions do not need to be answered too quickly. In fact, part of their beauty is that they slow us down. They remind us that science is not only a collection of facts, but a way of becoming more awake to the world. Science does not remove wonder from the universe. It gives wonder a sharper outline. It lets us see that the ordinary things around us are resting on extraordinary foundations. A glass of water, a beam of sunlight, the warmth of your own body, and the simple fact that atoms remain atoms are all part of a cosmic story that could have gone differently. The strange luck of being here is not a single miracle standing outside nature. It is a chain of physical conditions, each one connected to the next. The early universe had to produce the right starting material. Gravity had to gather that material into the first stars. Stars had to live, burn, and die. Later stars had to form from enriched clouds of gas and dust. Planets had to assemble from debris. Some worlds had to become stable enough for chemistry to continue without being erased too quickly. And on at least one world, chemistry crossed a threshold into life, and life eventually became conscious enough to study the universe that made it possible. There is humility in this. We do not yet know whether life is rare or common. We do not know whether intelligence is a frequent outcome of cosmic evolution or an unusual accident. We do not know whether the universe is one of many or whether its deepest laws could only have been this way. But we do know that the question is real. We do know that the existence of life depends on physics, chemistry, cosmic history, and time. And we do know that the universe has allowed at least one small region of matter to become aware of the whole. That is where this journey begins. Not with certainty, but with astonishment. As you settle into this thought, there is no need to solve the mystery tonight. You can simply rest inside it for a while. The universe is vast, the questions are deep, and for now, all you have to do is breathe, listen, and let the day quietly drift away. Chapter 2. The Laws That Had to Be Just Right. Before life could ever appear, before planets could cool or oceans could gather, the universe first needed something quieter and more basic, laws that behaved in a consistent way. This may sound obvious because consistency is deeply built into our experience. A stone falls when you drop it. Light travels across a room. Heat moves from warmer things toward cooler things. Atoms do not suddenly forget how to be atoms. The same kind of matter that exists inside your body also exists in distant stars, ancient rocks, and clouds of gas between galaxies. Reality has rules, and those rules remain stable enough for complexity to build upon them. But this stability is not something to take for granted. A universe with no reliable laws would not simply be strange. It would be unable to develop lasting structure. If the rules changed wildly from place to place or moment to moment, atoms could not preserve their identity. Chemistry could not accumulate, stars could not burn steadily, and memory itself would have no foundation. Life needs more than matter. It needs matter that can depend on the same physical behavior again and again. The laws of physics are not like human laws, written somewhere and enforced from outside. They are descriptions of how nature behaves. They describe relationships, how mass shapes motion through space and time, how electric charge responds to electromagnetic fields, how particles combine or separate, how energy moves, and how matter changes form while still obeying deeper patterns. These laws do not command nature from above. They are the regularities we find when we carefully observe what nature does. At the foundation of ordinary reality are a few basic interactions. Gravity pulls matter together across great distances. Electromagnetism governs light, electricity, magnetism, atoms, molecules, and nearly all the everyday contact forces we feel. The strong nuclear force binds quarks inside protons and neutrons, and also helps hold atomic nuclei together. The weak nuclear force allows certain particles to transform, making radioactive decay and important stellar processes possible. Together, these interactions shape the universe from the smallest known particles to the largest cosmic structures. Gravity is the most familiar on human scales, even though it is far weaker than the other forces at the level of particles. Its weakness is not a flaw. In a universe where gravity were much stronger, matter could gather too violently, stars might burn through their fuel too quickly, and stable planetary environments could become harder to maintain. In a universe where gravity were much weaker, gas might struggle to collapse into stars and galaxies. Gravity must be patient enough to build structure, but strong enough to begin the building. Electromagnetism is the force of chemistry. It holds electrons around atomic nuclei. It allows atoms to bond with other atoms. It gives shape to molecules, crystals, cells, rocks, water, air, and living tissue. When you touch a table, the sensation of solidity is not mainly the atoms of your hand physically merging with the atoms of the table. It comes from electromagnetic interactions between the outer electrons of nearby atoms. The world feels solid because electric charge has rules. For life, this is essential. Chemistry must be rich but stable. Molecules need to form, break, twist, fold, and react. They need enough flexibility to create complexity, but enough reliability to preserve information. The molecules of life depend on the fact that electrons occupy allowed arrangements around atoms, that bonds have certain strengths, and that energy can move through chemical systems in controlled ways. If electromagnetism were very different, familiar chemistry could be impossible. The strong nuclear force works in a realm far smaller than any cell or grain of dust, but its influence reaches everywhere. Protons contain positive electric charge, so they repel one another. In an atomic nucleus, that repulsion would tend to push them apart. The strong force overcomes this repulsion at very short distances, allowing nuclei to exist. Without it, the periodic richness of matter would disappear. There would be no stable carbon, oxygen, nitrogen, calcium, iron, or many of the elements that make planets and bodies possible. This force also matters inside stars. Stars shine because atomic nuclei can fuse under extreme conditions, releasing energy. Fusion is not simply a fire in the ordinary sense. It is a nuclear process tied to the structure of matter itself. If the nuclear forces were arranged differently, stars might not shine steadily, or they might not create the elements needed for rocky worlds and living chemistry. A universe can have matter and still lack the kind of long, slow stellar engines that prepare matter for life. The weak nuclear force is easier to overlook because it does not shape ordinary objects in the direct way electromagnetism does. Yet it is deeply important. It allows certain transformations among particles, and those transformations affect how stars begin their fusion processes. It also plays a role in radioactive decay and in the behavior of elusive particles called neutrinos. The weak force helps make the universe dynamic at a subatomic level. The delicate part is not that each force exists separately, it is that they coexist in a workable balance. Gravity can gather gas into stars. Nuclear forces can let stars shine. Electromagnetism can let atoms form molecules. The weak force can allow specific particle changes that matter for stellar reactions and cosmic evolution. Change one part enough, and the whole pattern might shift. Not every small change would necessarily destroy all possibility of complexity, and scientists are careful not to exaggerate what is known. But many studies of physical constants suggest that the space of life-friendly possibilities is not unlimited. A constant of nature is a quantity that appears to remain the same wherever and whenever we measure it. Some constants set the scale of forces. Some shape the behavior of particles. Some define the relationship between energy, matter, space, and time. These constants are not knobs that someone has found on a machine, but they can be imagined that way for the purpose of thought. If a knob were turned far enough, the behavior of the universe could change dramatically. The speed of light is one example of a deeply important constant. It is not only the speed at which light travels through empty space, it is woven into the structure of space and time themselves. It sets a cosmic speed limit for information and cause. Because signals cannot travel instantly everywhere, events have horizons, sequences, and relationships. Cause comes before effect in a meaningful way. Quantum mechanics adds another layer of precision. In the quantum world, particles do not behave like tiny versions of everyday objects. Their behavior is described by probabilities, allowed energy levels, wave-like patterns, and interactions that can seem deeply unfamiliar. Yet without quantum rules, atoms would not have stable structure. Electrons would not arrange themselves into the patterns that make chemistry possible. Matter would not have the layered architecture that allows complexity to grow from simplicity. This is one of the quiet miracles of physics. The rules that seem strange at the smallest scales are exactly the rules that make ordinary reality possible. The stability of a chair, the color of a leaf, the glow of a star, and the chemistry inside a cell all depend on quantum behavior. The world feels continuous and solid to us, but underneath that familiar surface is a set of precise restrictions on what particles can do. The universe also depends on conservation laws. Energy, momentum, electric charge, and other quantities follow patterns of preservation through change. Things can transform, but transformation is not chaos. Conservation gives nature a kind of accounting system. It allows change to happen without everything becoming arbitrary. For life, this matters because living things are controlled flows of energy and matter. A cell is not a static object. It is an organized process, constantly exchanging material and energy with its surroundings. This is why the fine structure of physical law is so important. Life is not simply a lucky arrangement of atoms. It is an arrangement of atoms inside a lawful universe. Atoms matter because the laws allow them to exist. Chemistry matters because the laws allow bonds and reactions. Stars matter because the laws allow gravity and nuclear fusion to work together. Time matters because the laws allow processes to unfold in ordered sequences. And still, we should remain careful. The phrase, "just right," can sound as if physics already proves that the universe was designed with life in mind. It does not. Science shows that the laws and constants we observe are compatible with life, and that many different possibilities would not be. But the deeper reason for these laws remains unknown. They may arise from principles we have not yet discovered. They may be part of a larger cosmic picture. They may be necessary in ways we do not yet understand. That uncertainty is not a weakness. It is what makes the question so powerful. The universe does not only contain things, it contains order. It contains patterns that repeat across distance and time. The same laws that shape a spark of electricity also help describe light from distant stars. The same gravity that holds your feet to the ground also guides galaxies through space. The same quantum rules that structure atoms in your body also govern matter in the oldest light we can observe. This unity is one of the deepest discoveries of science. Reality is not a collection of separate mysteries. It is one connected system. And within that system, life became possible. So as this chapter closes, let the thought become simple again. Beneath the noise of the day, beneath worry and motion and unfinished tasks, there is a universe held together by patient laws. For now, you do not need to understand all of them. You can simply rest in the quiet fact that they are there, steady enough to hold the stars and gentle enough to hold you. Chapter 3. Gravity, the gentle force that built the cosmos. Gravity is the quiet architect of the universe, the force that took a nearly uniform early cosmos and slowly shaped it into galaxies, stars, planets, and the stable worlds where life could begin. To us, gravity feels simple. It is the pull that keeps our bodies on the ground, the reason rain falls, the reason a dropped object does not drift upward into the sky. It is so constant and familiar that we rarely notice it unless it becomes unusually strong, as when we climb a hill, lift a heavy bag, or watch the tide move under the influence of the moon. But on cosmic scales, gravity is not merely a downward pull. It is the great organizer of matter. In the older Newtonian picture, gravity can be imagined as an attraction between masses. Every object with mass pulls on every other object with mass. A planet pulls on a moon. A star pulls on a planet. A galaxy pulls on its stars. This picture is still useful for many everyday calculations and for understanding much of orbital motion. But modern physics gives gravity a deeper meaning. According to general relativity, matter and energy shape space-time, and objects move through that curved space-time. The Earth does not orbit the Sun because it is attached to an invisible string. It follows a path through a curved cosmic geometry shaped mostly by the Sun's mass. This idea can sound abstract, but its consequences are very real. Gravity bends the path of light. It slows time near massive objects. It allows black holes to exist. It creates the large-scale motion of galaxies and clusters of galaxies. It is not just one effect among many. It is part of the structure of the universe itself, and yet gravity is also strangely gentle. Compared with the other fundamental interactions, gravity is extraordinarily weak at the scale of individual particles. A tiny magnet can lift a metal object against the gravitational pull of the entire Earth. Electric forces between charged particles are far stronger than gravitational forces between the same particles. But gravity has an advantage that the other forces do not have in the same way. It adds up. There is no negative mass that cancels ordinary mass in the way positive and negative electric charges can cancel. Large collections of matter produce large gravitational effects, and across the vastness of space, gravity becomes dominant. This is why gravity could build the cosmos. The early universe was not perfectly smooth. It was extremely even, but not completely even. There were tiny differences in density, small regions where matter was slightly more concentrated than in nearby regions. These differences were incredibly slight, but gravity is patient. A region with a little more matter had a little more gravitational pull. It attracted more material toward itself. As it gained material, its pull became stronger. Over immense stretches of time, small differences grew into large structures. This process is called gravitational instability, but the idea is simple. If one part of a cloud is slightly denser than another, gravity can help that denser part gather more matter. The rich get richer in a physical sense. The universe began with faint unevenness, and gravity amplified that unevenness into structure. Dark matter played a crucial role in this process. Dark matter does not shine, absorb light, or form atoms in the ordinary way. We know it mainly through its gravitational influence. In the early universe, dark matter helped form invisible scaffolding, regions of gravitational attraction where ordinary matter could later gather. Gas fell into these gravitational wells, heated, cooled, collapsed, and eventually helped form the first stars and galaxies. Without the gravitational influence of dark matter, the growth of structure would likely have been very different. This is one of the reasons gravity is so important to the question of life. Life needs planets, and planets need stars, and stars need dense clouds of gas to collapse. Those clouds do not collapse simply because matter exists. They collapse because gravity can overcome pressure, motion, turbulence, and heat in certain regions. Gravity must be strong enough to pull matter inward, but not so overwhelming that everything collapses too quickly into extreme states. A star begins in a cold, dense region of gas and dust, often inside a much larger molecular cloud. At first, the cloud is thin by Earth standards, but in space, it can contain enormous amounts of material. Gravity slowly draws part of the cloud inward. As the material falls, it becomes denser. As it becomes denser, it heats up. A young object forms at the center, surrounded by a disk of leftover material. Eventually, if the central object becomes hot and dense enough, nuclear fusion begins. A star is born. This is one of gravity's most beautiful balances. Gravity tries to pull the star inward. Energy from fusion pushes outward. For much of a star's life, these two tendencies can settle into a stable state. The star does not immediately collapse under its own weight, and it does not instantly explode outward. It shines. It stays luminous for long enough to warm planets, drive weather, support chemistry, and give life time to develop. The sun is an example of this balance. It is not burning like a campfire. It is held together by gravity, while nuclear reactions in its core release energy that slowly travels outward and eventually reaches space as light. Earth receives a small portion of that light, and that small portion is enough to help power the biosphere. Photosynthesis, climate, ocean circulation, food chains, and the rhythm of day and night all depend indirectly on the gravitational stability of a star. Gravity also helps make planets. Around young stars, leftover gas and dust can flatten into a rotating disk. Within that disk, tiny grains collide and stick together. Over time, small pieces become larger bodies, and larger bodies gather more material through their own gravity. The process is not smooth or gentle at every stage. It includes impacts, migrations, heating, and loss. But gravity makes accumulation possible. It allows scattered dust to become stones, stones to become planetesimals, and planetesimals to become planets. Once a planet exists, gravity continues shaping its habitability. A world needs enough gravity to hold an atmosphere, but not so much that it becomes something entirely different from a rocky planet with accessible surface conditions. Gravity influences whether a planet can keep gases near its surface, whether liquid can collect in basins, how mountains rise and erode, how interiors separate into layers, and how moons and tides affect planetary environments. Gravity is not the only factor, but it is always present. On an even larger scale, gravity binds galaxies. A galaxy is not just a random spray of stars. It is a gravitational system containing stars, gas, dark matter, planets, stellar remnants, and often a massive black hole near its center. Gravity shapes spiral arms, stellar orbits, galactic mergers, and the slow movement of matter through cosmic time. It gathers galaxies into groups and clusters. It stretches across distances so large that light itself takes vast ages to cross them. Gravity can also act like a lens. When light from a distant object passes near a massive galaxy or cluster, the curvature of space-time can bend that light. The distant object may appear distorted, stretched, or magnified. This effect allows astronomers to study objects that would otherwise be too faint or too far away to see clearly. In this way, gravity does not only build the universe, it also helps reveal it. But gravity's gentleness is part of the fine-tuning mystery. If gravity were much stronger relative to the other forces, stars could be smaller, hotter, and shorter-lived. Matter might collapse into dense objects more easily. Planetary systems might be less stable over long periods. If gravity were much weaker, the gathering of matter into stars and galaxies could be harder or slower, and the universe might remain too diffuse for rich cosmic structure to form in the same way. The exact consequences depend on many other constants and conditions, so this is not a simple one-knob problem. Still, life as we know it depends on gravity being strong enough to build, yet gentle enough to allow time. That word time matters deeply. Life is not only a question of ingredients, it is a question of duration. Stable stars need time to shine. Planets need time to cool. Atmospheres need time to evolve. Chemistry needs time to explore possibilities. Biology needs time to become more complex. Gravity in our universe does not merely crush everything immediately. It gathers slowly, it builds stages, it creates arenas where long histories can unfold. This makes gravity feel almost paradoxical. It is the force behind collapse, yet also the force behind structure. It pulls clouds inward until stars ignite. It draws worlds together from dust. It binds galaxies, but also guides planets in stable orbits. It can create black holes, but it also creates the conditions for sunlight. It can destroy, but without it, the universe might never have built anything dense enough to matter. So when we speak of the universe being strangely suitable for life, gravity is one of the first reasons. It did not have to behave in a way that made stars possible, or planets stable, or galaxies long-lived. Yet in our universe, gravity works with remarkable patience. It turns small beginnings into enormous structures. It allows matter to gather without always ending in immediate ruin. It gives the cosmos shape. And here, on a small planet held gently near a steady star, we live inside gravity's long work. Every breath happens within its quiet field. Every ocean rests in its basin because gravity holds it there. Every night sky is a record of gravity's ancient patience, written in stars. For now, let that thought become soft. You do not need to carry the whole universe in your mind. Gravity is already carrying you, calmly and without effort, while the earth turns beneath the darkness and the stars continue their slow, silent motion. Chapter 4. The nuclear balance inside every star. A star looks peaceful from far away, but inside it, the possibility of life depends on an extraordinary balance between crushing gravity, rising pressure, and nuclear reactions occurring in a core no human eye can ever directly see. From Earth, starlight seems gentle. It crosses space as a quiet glow touches clouds, reflects from oceans, warms skin, and marks the slow passage of night into morning. But the light of a star is not simple. It is the final outward sign of a deep process that begins under conditions far beyond ordinary experience. A star is not burning in the way wood burns in a fireplace. Wood burns because atoms rearrange through chemical reactions. A star shines because atomic nuclei are transformed. Its light comes from the inner structure of matter itself. At the center of a star, temperature and pressure become extreme. Matter is squeezed so tightly that atoms no longer behave as complete atoms with neat outer electrons. Instead, much of the material becomes plasma, a state in which nuclei and electrons move separately in a hot, charged sea. In that environment, hydrogen nuclei rush through the core at enormous speeds. They are all positively charged, so they naturally repel each other. Under ordinary conditions, that repulsion keeps them apart. But in a stellar core, collisions happen constantly, and quantum physics allows some nuclei to get close enough for the strong nuclear force to take over. This is one of the most important thresholds in the universe. The strong nuclear force acts only at extremely short distances. But when nuclei come close enough, you can bind them together. In stars like the Sun, hydrogen is gradually converted into helium through a chain of reactions. The details involve several steps, but the essential idea is clear. Lighter nuclei combine into heavier nuclei, and a small amount of mass is released as energy. That energy spreads outward through the star, eventually becoming the light and heat that space receives. This process is called nuclear fusion, and it is the engine behind most of the stars we see. Fusion is not just a source of brightness, it is a source of balance. Gravity pulls the star inward, trying to compress it. Energy from fusion heats the stellar gas, creating pressure that pushes outward. For a long period in a stable star's life, these two tendencies balance each other. This state is called hydrostatic equilibrium. It does not mean that nothing is happening. A star in equilibrium is intensely active inside. Particles move, radiation scatters, magnetic fields shift, and nuclear reactions continue. But as a whole, the star remains stable, neither collapsing rapidly nor flying apart. For life, this stability matters more than almost anything. A star that changes too violently cannot give planets a long, steady supply of energy. A star that burns through its fuel too quickly may not allow enough time for complex chemistry and biology. A star that is too unstable may strip atmospheres, sterilize surfaces, or flood nearby worlds with dangerous radiation. Life does not need a star to be perfectly calm, but it does need the star's behavior to remain within workable limits for long stretches of time. The Sun is especially important to us because it is stable on biological timescales. Its energy output changes, but not wildly enough to erase Earth's surface conditions from one moment to the next. Deep inside it, fusion proceeds at a pace controlled by temperature, pressure, and the probability of nuclear reactions. This pace is not explosive like a bomb. It is slow and regulated by the physics of the core. The Sun releases a tremendous total amount of energy because it is so large, but each small region of its core produces energy in a surprisingly measured way. That measured pace is part of why a planet like Earth can exist with oceans, weather, and life. Sunlight is not simply brightness, it is usable energy arriving in a long-lasting flow. Plants and other photosynthetic organisms can capture a portion of that energy and use it to build chemical structures. Climate systems can move heat around the planet. Water can cycle between ocean, air, ice, and rain. Every living system on Earth is connected, directly or indirectly, to the nuclear balance inside our star. But not all stars are like the Sun. A star's mass strongly affects its inner life. Lower mass stars tend to burn their fuel slowly. Some can shine for far longer than the current age of the universe. Very massive stars, by contrast, are brighter and hotter, but they consume their fuel much faster. This can seem surprising at first. A massive star has more fuel, so it might seem as if it should live longer. But greater mass creates higher pressure and temperature in the core, which drives fusion at a much faster rate. The star spends its fuel with enormous intensity. This matters for habitability. A stable energy source needs not only warmth, but duration. Complex life, at least as we understand it from Earth, requires long periods of environmental continuity. Worlds need time for crusts to cool, atmospheres to change, oceans to persist, and chemistry to explore many possible pathways. Stars that live too briefly may die before nearby planets have much opportunity to become biologically rich. Stars that are too active or variable may make surface environments difficult. The question is not simply whether a star shines. It is whether it shines in a way that allows time to become meaningful. The nuclear balance inside stars also determines what the universe is made of. Hydrogen fusion creates helium, but later stages of stellar life can create heavier elements. In stars with enough mass, helium can fuse into carbon, and further processes can build oxygen, neon, magnesium, silicon, sulfur, and eventually elements around iron. The exact pathway depends on the mass and stage of the star. Smaller stars and larger stars do not have the same internal futures. Some end quietly, releasing enriched outer layers into space. Others die in violent explosions that scatter newly formed elements across interstellar clouds. This is where the inner physics of stars connects directly to planets and bodies. Carbon is central to organic chemistry. Oxygen is part of water and rocks. Nitrogen is essential in biological molecules. Phosphorus helps store and transfer energy in living cells. Iron plays roles in planetary cores and in blood. These elements were not simply waiting in abundance at the beginning. They had to be produced through cosmic processes, many of them connected to stars. The production of carbon is especially important in discussions of cosmic fine-tuning. Carbon forms in stars through a delicate nuclear pathway involving helium nuclei. The process depends on specific energy states inside atomic nuclei. If those nuclear properties were significantly different, the amount of carbon made by stars could change greatly. Oxygen production is connected to this balance as well. Because life as we know it depends on carbon chemistry and water, the way stars manufacture carbon and oxygen has become one of the most famous examples of how deeply life is tied to nuclear physics. This does not mean the universe was intentionally adjusted for carbon. Science does not need to make that claim. But it does show that the presence of life depends on very specific physical behavior inside stars. The conditions that make stars shine are not separate from the conditions that make chemistry rich. The same nuclear rules that hold stellar cores in balance also help decide whether the universe will contain the elements needed for living worlds. There is also a limit to fusion as an energy source. Fusion of lighter elements can release energy, but this process changes as nuclei become heavier. Around iron, fusion no longer provides energy in the same helpful way for a star. For massive stars, this creates a crisis near the end of life. Once the core can no longer support itself through energy-producing fusion, collapse can follow. The result may be a supernova, a neutron star, or a black hole, depending on the star's mass and conditions. Even this destructive ending can become creative on cosmic timescales because it spreads elements into space and helps seed future generations of stars and planets. So the balance inside stars is not only a balance of inward and outward forces, it is also a balance between stability and transformation. Stars must remain steady long enough to support planets, but they must also change over cosmic time to enrich the universe. If all stars lived forever without releasing heavier elements, rocky worlds like Earth might never form. If all stars died too quickly, there might be no long eras of steady light. The universe needs both patience and renewal. This is why stars are so central to the mystery of a life-permitting cosmos. They are not merely light scattered across the dark. They are nuclear engines, element factories, gravitational systems, and clocks of cosmic history. Their cores translate the laws of physics into warmth, chemistry, and time. They make the darkness visible. They prepare the raw materials from which planets and living things can eventually emerge. And on Earth, we live within the influence of one ordinary star whose internal balance has remained stable enough for life to unfold. Every sunrise is the surface expression of nuclear events deep inside the sun. Every plant leaf, every breath of oxygen, every warm afternoon, and every ancient fossil carries the memory of stellar balance. As this thought settles, there is no need to hold its full complexity all at once. Somewhere above the quiet turning of the earth, the sun continues its steady work. Its light has already crossed the darkness for you, and for now, you can let that distant balance become a calm place to rest. Chapter 5. Carbon, Oxygen, and the Chemistry of Living Worlds. If gravity built the stages and stars filled them with light, chemistry is where the universe became intimate, turning ancient atoms into oceans, rocks, air, cells, and eventually the living worlds able to notice the sky above them. A planet can orbit a stable star and still remain lifeless. It can have sunlight, seasons, mountains, and storms, yet never develop the kind of molecular complexity that biology needs. Life requires more than warmth. It requires ingredients that can combine, separate, store information, move energy, and rebuild themselves through time. This is why carbon, oxygen, and the wider chemistry of living worlds matter so deeply. They are not decorative details in the cosmic story. They are the bridge between physics and biology. Carbon is often called the backbone of life because it has an unusual talent for connection. A carbon atom can bond with several other atoms at once, and it can bond strongly with other carbon atoms. This allows carbon to form chains, rings, branching structures, sheets, and complex three-dimensional shapes. In chemistry, shape matters. A molecule is not only a collection of atoms, it is a structure with angles, surfaces, charges, and movement. Its shape helps determine what it can do, what it can react with, and how it can fit into larger systems. This makes carbon especially useful for building complexity. It can form small molecules, but it can also form enormous biological molecules, with repeating patterns and precise functions. The molecules that store genetic information, the molecules that form cell membranes, the molecules that build proteins, fats, sugars, pigments, hormones, and many other biological structures all depend on carbon chemistry. Other elements can also form complex compounds, but carbon has a rare combination of stability and flexibility. It can hold together well enough for structures to persist, yet it can also participate in reactions that allow change. That balance is essential. If chemical bonds were too weak, molecules would fall apart too easily. If they were too strong, chemistry would become rigid and lifeless, unable to rearrange itself. Living systems depend on bonds that can be stable in one setting and changeable in another. A cell must preserve its identity, but it must also react, repair, grow, divide, and use energy. Carbon chemistry makes this kind of controlled complexity possible. Oxygen is just as important, though in a different way. Oxygen is highly reactive, which means it can take part in many energy-rich chemical processes. It is a major part of water, rocks, minerals, carbon dioxide, and countless biological molecules. In your body, oxygen is not only the gas you breathe, it is built into the water inside you, the sugars that fuel cells, the molecules that help release energy from food, and the mineral structures that support bones. Yet oxygen also teaches us an important lesson. An ingredient can be useful and dangerous at the same time. Free oxygen gas is powerful because it reacts so readily. For many organisms on Earth, oxygen allows highly efficient energy use. But reactive oxygen can also damage delicate molecules. Early life on Earth did not begin in an atmosphere rich in oxygen gas. For a long time, Earth's atmosphere contained very little of it. The later rise of oxygen was linked to photosynthetic organisms that released oxygen as a waste product, slowly changing the planet's air, oceans, rocks, and biological possibilities. This means oxygen was not simply present from the beginning as a gift waiting for animals to breathe. It became abundant because life itself transformed the planet. Chemistry shaped life, and then life reshaped chemistry. This feedback is one of the most important ideas in understanding living worlds. A habitable planet is not just a stage where life appears. If life becomes widespread enough, it can become part of the planet's geology, atmosphere, and climate. Water sits at the center of this story. Water is not alive, but it is extraordinarily useful for life as we know it. It can dissolve many substances, allowing atoms and molecules to move, meet, and react. It remains liquid across a range of temperatures that can exist on planetary surfaces. It helps transport nutrients. It stores and moves heat, softening temperature changes. It participates directly in many biological reactions. Its properties come from the way hydrogen and oxygen bond and from the uneven distribution of electric charge within each molecule. This uneven charge makes water a powerful solvent. It can surround ions and polar molecules, pulling them into solution and allowing chemistry to happen in a fluid environment. In a dry, motionless solid, molecules may be locked in place. In liquid water, they can drift, collide, fold, unfold, separate, and recombine. For life, that mobility is precious. It allows chemical systems to become dynamic rather than frozen. But water alone is not enough. A world can have water and still not be alive. Life also needs usable energy, chemical nutrients, and conditions that remain stable long enough for complexity to develop. A frozen ocean locked beneath ice may still be interesting if there is energy and chemistry below the surface. A warm, shallow sea may be promising if it contains the right minerals and cycles. A planet with water but no useful chemistry may remain sterile. Habitability is not one condition. It is a relationship among many conditions. Carbon and oxygen often work together through carbon dioxide. Carbon dioxide is a simple molecule, but it plays enormous roles in planetary climate and life. In an atmosphere, it can trap heat and help keep a planet warm enough for liquid water. Too little can make a planet colder. Too much can contribute to extreme greenhouse conditions. On Earth, carbon dioxide also moves through long-term cycles involving air, oceans, rocks, volcanoes, and living organisms. This movement helps connect the atmosphere to the deep planet and to the biosphere. Over long timescales, Earth's climate has been influenced by the exchange of carbon among the atmosphere, oceans, rocks, and living systems. Weathering can draw carbon dioxide out of the air. Volcanic activity can return it. Organisms can store carbon in shells, sediments, forests, and soils. No single process controls everything, but together they create a planet where chemistry is constantly cycling. A living world is not chemically still. It breathes in a geological sense, slowly moving elements through many forms. Other elements matter as well. Hydrogen is part of water and organic molecules. Nitrogen is needed for proteins and genetic chemistry. Phosphorus is important for energy transfer and information-bearing molecules. Sulfur appears in certain amino acids and in many microbial energy systems. Metals such as iron, magnesium, copper, zinc, and manganese help enzymes perform chemical tasks. Life is carbon-based, but it is not made of carbon alone. It is a collaboration among elements. This collaboration depends on availability. Elements may exist somewhere in a planet, but life needs access to them in usable forms. A nutrient trapped forever deep inside a planet cannot easily support surface biology. A gas lost to space cannot shape an atmosphere. A mineral that never dissolves may be chemically unavailable. Living worlds require not only ingredients, but circulation. Oceans that move, rocks that weather, atmospheres that exchange gases, interiors that release material, and perhaps tectonic or volcanic activity that renews chemical supplies. This is where planetary chemistry becomes more than a recipe. It becomes a system. The surface, atmosphere, ocean, crust, interior, and living things can interact. Sunlight can drive reactions near the surface. Heat from inside the planet can power chemistry in deep environments. Impacts, erosion, freezing, melting, evaporation, and volcanic gases can all shift what chemistry is possible. Life, if it appears, may then join this network and alter it from within. The phrase living world should be used carefully. Earth is the only known example of a planet with life. Scientists search for other living worlds by looking for environments where chemistry, energy, and stability might overlap. They study planets around other stars, icy moons with subsurface oceans, ancient rocks, atmospheres, and chemical signatures that could suggest biological activity. But there is no simple test that says a world must be alive. A planet can look promising and still be empty. Another could hide life in ways difficult to detect. Still, Earth shows what is possible when the chemistry works. Carbon can build complex frameworks. Oxygen can help shape water, rocks, air, and energy flow. Water can provide a fluid setting for reactions. Other elements can fill specialized roles. Energy can move through the system. Over time, chemistry can become organized enough to preserve patterns, copy information, and evolve. This is why the chemistry of living worlds belongs in the mystery of a universe suited for life. The universe did not only need stars. It needed stars that could enrich space with useful elements. It needed planets where those elements could gather. It needed physical laws that allow bonds, reactions, liquids, minerals, atmospheres, and energy gradients. And it needed enough time for simple chemistry to become something deeper. When you look at a leaf, a shell, a cloud, or your own hand, you are not seeing ordinary matter in an ordinary arrangement. You are seeing cosmic chemistry that found a way to become delicate. The same universe that makes galaxies also permits molecules that fold, cells that divide, oceans that circulate, and living beings that wonder where their atoms came from. For now, let that thought become quiet rather than overwhelming. The chemistry of life is not separate from you. It is gently happening inside you with every breath. As the day loosens its hold, you can rest in the simple fact that for this moment, the atoms of the universe are arranged as you, warm, breathing, and safe enough to drift towards sleep. Chapter 6. The universe that expands at the right pace. The universe is not merely a place where things exist. It is a place whose very space has been stretching for almost all of cosmic history, and that stretching had to follow a remarkably careful path for galaxies, stars, planets, and life to appear. When people first hear that the universe is expanding, it is tempting to imagine an explosion throwing galaxies outward into empty space. But that picture is not quite right. The expansion of the universe is not simply matter flying away from one central point. It is space itself changing. Distant galaxies are not all rushing through space from a single cosmic center. Rather, the space between large-scale structures is growing, so that, on average, very distant galaxies become farther from one another over time. There is no known central point from which the whole universe expanded. Wherever an observer is located, distant galaxies appear to recede in a pattern connected to the expansion of space. This does not mean every object is expanding internally. Your body is not expanding. The Earth is not expanding. The solar system is not expanding. Galaxies themselves are held together by gravity. Expansion becomes most important across enormous distances where local gravitational binding no longer dominates. This idea already changes the feeling of the universe. Space is not just a passive stage, it has history, it has behavior. It can stretch, cool, and carry light from ancient times into the present. The universe we see today is not only a collection of objects. It is the result of a long relationship between matter, radiation, gravity, and expansion. In the earliest hot, dense state of the universe, matter and radiation were packed together far more tightly than they are now. The universe was not full of stars or planets. It was a hot, bright, rapidly changing environment of particles and energy. As space expanded, the contents of the universe spread out and cooled. Cooling was essential. Without it, particles could not settle into the forms that later made atoms possible. If the universe had remained too hot and dense for too long, the familiar structures of matter could not have emerged. Expansion gave the universe room to change. As the universe cooled, simple atomic nuclei formed. Then later, when conditions became cool enough, electrons could join with nuclei to make neutral atoms. Once that happened, light could travel more freely through space. The oldest light we can observe today comes from this early transition. It arrives from every direction as a faint background glow, stretched by the expansion of space into microwave radiation. This ancient light is one of the clearest pieces of evidence that the universe began in a much hotter, denser state and has been expanding and cooling ever since. But cooling alone was not enough. the universe also needed matter to gather. Gravity tried to pull matter into denser regions, while expansion carried regions of space away from one another. The future of structure depended on the balance between these tendencies. If expansion had been too rapid in the wrong way, matter could have been pulled apart before gravity had enough time to gather it into galaxies. The universe might have become thin, cold, and almost featureless, filled with particles and radiation, but lacking the great cosmic structures needed for stars. If expansion had been too slow, a different problem could have appeared. Gravity might have overwhelmed expansion too early, causing the universe to collapse back on itself before stars and planets could develop over long periods. In such a universe, there might be no stable cosmic history, no generations of stars, no enrichment of space with heavier elements, and no patient environments where chemistry could deepen into life. The real universe seems to have followed a middle path. It expanded quickly from an early dense state, but not in a way that erased structure completely. Tiny unevenness in the early universe survived. Gravity slowly amplified those uneven regions. Dark matter helped shape the invisible gravitational framework where ordinary matter could later collect. Over time, galaxies formed, stars ignited, and planets became possible. This does not mean the expansion rate was chosen for life. It means that the expansion history we observe is compatible with a long, structured universe. It allowed enough cooling for atoms, enough time for gravity, and enough stability for cosmic complexity. That compatibility is part of the fine-tuning question. The universe can obey laws and still fail to produce the conditions life needs if its overall expansion history is very different. One of the most striking features of our universe is that its geometry appears to be very close to flat on the largest observable scales. In simple language, this means that space, when averaged over enormous distances, behaves very nearly like the kind of geometry we learn from ordinary experience, rather than being strongly curved in a way that would make the universe quickly collapse or expand in a very different manner. This near flatness is connected to the balance between the total contents of the universe and the expansion of space. Cosmologists have long recognized that this balance is surprising. In many simple models, a universe that begins even slightly away from the right overall balance can move farther away from it as time passes. The fact that our universe still appears so close to flat after such a long history is one reason the idea of cosmic inflation became important. Inflation suggests that, extremely early on, the universe went through a brief period of incredibly rapid expansion. This could help explain why the observable universe looks so uniform and flat, while also stretching tiny quantum fluctuations into the seeds of later cosmic structure. Inflation is a powerful idea, but it is still an area of active research. Scientists have strong reasons to take it seriously, yet they continue to study its details and possible alternatives. For this chapter, the most important point is simple. The earliest expansion of the universe matters. It shaped the starting conditions for everything that followed. The pattern of expansion helped decide whether the universe would become structured, smooth, long-lived, or short-lived. Expansion also affects light itself. As space stretches, light traveling through it is stretched as well. Its wavelength becomes longer and its energy becomes lower. This is why distant galaxies often appear redshifted, meaning their light has been stretched toward longer wavelengths by cosmic expansion. By measuring this stretching, Astronomers can study how fast the universe has been expanding at different times. The light from distant galaxies is not only an image of where they are, it is a record of how space has changed while that light traveled. This gives us a kind of cosmic memory. When we look far into space, we also look back in time, because light takes time to reach us. The deeper we look, the older the light. Galaxies seen at great distances show us earlier chapters of the universe. The oldest background light shows us the universe before stars and galaxies existed. Expansion turns the sky into a history book, with each distance preserving a different era. There is another quiet consequence. Because the universe expands, it also changes the future. Distant galaxies can eventually move beyond the limits of what light can reach us from, not because they are moving through space faster than light in a local sense, but because the space between us and them stretches. Cosmic expansion creates horizons. It decides what can be seen, what can influence what, and what parts of the universe will remain forever beyond observation. This is why expansion belongs in the story of life. Life does not arise in an unchanging container. It arises inside a universe with a specific history of cooling, stretching, clumping, and accelerating. Expansion helped make room for atoms, galaxies, stars, and planets. It also prevented everything from collapsing too early. It gave gravity a stage large enough to work across time, and it gave chemistry a universe old enough to become interesting. Today, the expansion of the universe is accelerating, driven by what we call dark energy. This will be explored more deeply in the next chapter, because it brings its own fine-tuning mystery. For now, it is enough to see that expansion was never a minor background detail. It has shaped the past, the present, and the possible future of everything. The strange luck is not only that matter exists, or that stars shine, or that carbon can form delicate molecules. It is also that the universe expanded in a way that allowed all those things to happen in sequence, not too quickly to prevent structure, not too slowly to end the story before it began, not too chaotic to erase pattern, not too empty to leave matter forever scattered. As you rest with this thought, the expansion of the universe can feel less like a violent motion and more like a slow opening. Space has been unfolding for ages beyond imagination, and within that unfolding, there was time for one small world to form, cool, breathe, and become home. You do not have to chase that vastness tonight. Let it widen gently around you while the day becomes smaller, softer, and easier to release. Chapter 7: Dark Energy and the Quiet Acceleration of Space. For most of cosmic history, gravity seemed like it should be slowly pulling back on the expansion of the universe. Yet the most careful observations revealed something stranger. Space is not merely expanding, it is expanding faster over time. This discovery changed modern cosmology. Before it, many scientists expected the expansion of the universe to be gradually slowing down. That expectation made sense. Matter attracts matter through gravity. Galaxies, clusters, gas, stars, planets, and dark matter all contribute gravitational influence. If the universe began by expanding, gravity should act like a brake, not because it stops everything locally, but because the total matter content of the cosmos should resist the outward stretching of space. For a while, the great question seemed to be how much the expansion was slowing. Was there enough matter to eventually reverse expansion and pull the universe back inward? Or would the universe keep expanding forever, gradually slowing but never quite stopping? These were already enormous possibilities. But then, observations of distant exploding stars suggested a third answer. The expansion was not slowing in the expected way. It had begun to accelerate. This is where dark energy enters the story. Dark energy is the name given to whatever is causing the accelerated expansion of the universe. The word dark does not mean it is shadowy or made of darkness in an ordinary sense. It means we do not see it directly as light, and we do not yet understand its nature. It is inferred from the way the universe expands, from the large-scale distribution of matter, from the oldest light in the universe, and from many other observations that fit together into a broad cosmological picture. The most important thing to understand is that dark energy is not simply another substance floating through space like dust or gas. In the simplest and most widely used model, it behaves more like an energy associated with space itself. As space expands, ordinary matter becomes more spread out. Radiation also becomes diluted and stretched. But dark energy, if it acts like a cosmological constant, does not thin out in the same way. Its density remains effectively constant as space grows. That means its influence becomes more important as the universe expands and matter becomes more diluted. This idea is strange, but it helps explain why acceleration began relatively late in cosmic history. In the early universe, matter was denser, and gravity from matter strongly affected the growth and motion of structures. Over time, expansion spread matter out. Dark energy did not fade in the same manner. Eventually, its influence became dominant on the largest scales, and the expansion of the universe began to speed up. This does not mean galaxies are being torn apart right now. The acceleration of space is mainly important across vast cosmic distances. Galaxies, solar systems, planets, and human bodies are held together by forces much stronger than the effect of cosmic expansion at those scales. The Milky Way is not swelling like a balloon. Earth is not being stretched. Your room is not expanding. Dark energy shapes the universe as a whole, not the bonds that hold ordinary objects together. Still, its influence is profound. It affects the future visibility of the cosmos. If acceleration continues indefinitely, distant galaxies beyond our local cosmic neighborhood will become harder and eventually impossible to observe. Their light will be stretched and weakened as space expands. In the far future, observers in our galaxy's descendants may see a much emptier sky, with most other galaxies beyond reach. The universe would still contain enormous structure, but much of it would vanish beyond cosmic horizons. This is one of the quietest forms of cosmic drama. Nothing explodes. Nothing announces the change with violence. Space simply continues to open. Distances grow. Light takes longer to cross the gaps. Regions of the universe slip beyond one another's view. Dark energy does not destroy the cosmos in a single moment. It changes the long-term meaning of connection. For the question of life, dark energy matters because its value appears to be extremely small, yet not zero. If the repulsive effect associated with dark energy had been much stronger in the early universe, space might have accelerated apart before matter could gather into galaxies. Without galaxies, there would be no long-lived stellar communities, no heavy element enrichment in the familiar sense, and no stable planetary systems like the one we inhabit. Matter would have been scattered too quickly for gravity to assemble the structures that life needs. If dark energy had been very different in another direction, the universe's expansion history could also have changed dramatically. A universe dominated too early by collapse or shaped by a different kind of cosmic energy might not produce the long, steady eras required for stars, planets, and chemistry. The exact possibilities depend on the full structure of physical law, so scientists are careful. But the basic point remains. The observed weakness of dark energy is one of the most striking puzzles in cosmology. It is sometimes called the cosmological constant problem. In simple terms, some ideas from quantum physics suggest that empty space should have an enormous energy associated with it. But the dark energy we infer from cosmic expansion is incredibly tiny by comparison. The mismatch between theoretical expectation and observed cosmic behavior is not a small bookkeeping issue. It is one of the deepest unsolved problems in physics. It tells us that our understanding of space, energy, gravity, and quantum theory is still incomplete. This makes dark energy different from many mysteries. It is not merely a missing object we hope to find with a better telescope. It may be telling us something fundamental about the nature of reality. Perhaps dark energy is truly a constant property of space. Perhaps it changes slowly with time. Perhaps it is connected to a field that fills the universe. Perhaps our theory of gravity needs refinement on the largest scales. Scientists are actively testing these possibilities by measuring how the expansion of the universe has changed through time and how cosmic structures have grown. Recent observations have made this question even more interesting. Some large surveys have found hints that dark energy may not behave exactly like a constant. These hints are not yet the final word. They need confirmation, comparison, and careful analysis. Cosmology is a field where small differences in measurement can matter greatly, and where many types of data must be made consistent with one another. But the possibility itself is exciting. If dark energy evolves, then the future of the universe may be more complex than the simplest model suggests. For this chapter, the most important point is not that we already know what dark energy is. We do not. The important point is that life exists in a universe where dark energy is weak enough to have allowed structure to form, yet strong enough to dominate the cosmic future. It waited, in a sense, while galaxies formed, stars lived, planets assembled, and chemistry deepened. Only later did it become the main influence over the expansion of space. That timing is remarkable. If acceleration had ruled too early, complexity might have been prevented. If the universe had collapsed too soon, complexity might have been cut short. Instead, there was a long middle era, an era in which gravity could build, stars could enrich, planets could cool, and life could emerge. Dark energy is part of the reason this era is not the final state, but it did not prevent the era from happening. There is something almost poetic in that. The force, or property, or field we understand least may have helped set the boundary conditions for everything we know. It is invisible to daily life, yet it shapes the fate of galaxies. It is almost unimaginably faint in any small region, yet across the vastness of space it becomes powerful. It is quiet, diffuse, and mysterious, but it may decide whether the far future is empty, slowing, or something stranger. Dark energy also reminds us to be humble about the word empty. Empty space is not necessarily nothing. In modern physics, space has structure, behavior, geometry, and perhaps energy of its own. A vacuum is not just an absence of objects. It can have properties that affect the motion of the universe. The greatest distances between galaxies are not merely blank backgrounds. They may be where one of the deepest mysteries of physics is quietly expressed. And so the universe that allows life is not just balanced by matter, stars, and chemistry. It is also balanced by the behavior of space itself. The expansion could not have been shaped carelessly. The energy of empty space, whatever it truly is, could not have overwhelmed the early formation of structure. Yet it also could not be ignored, because today it dominates the cosmic expansion. As you rest with this thought, let dark energy feel not frightening, but spacious. The universe is still opening, slowly and silently, beyond every horizon we can see. And here, inside that vast unfolding, you do not need to reach the edge of anything. You can simply let the night widen around you, while your breath becomes steady and the day fades into quiet distance. Chapter 8. The Anthropic Principle. Are we surprised because we exist? After exploring gravity, stars, chemistry, expansion, and dark energy, we arrive at a quieter but deeply unsettling question. Are the conditions of the universe truly surprising, or do they only seem surprising because only a universe like this could contain beings able to be surprised? This is the central idea behind the Anthropic Principle. At its simplest, it says that our observations of the universe are limited by the fact that we exist as observers. We should not expect to find ourselves in a universe where observers cannot exist. That sounds almost too obvious at first, like saying we can only wake up in a place where waking up is possible. But in cosmology, this simple point becomes powerful, because it changes how we think about apparent cosmic coincidences. Imagine asking why Earth has conditions suitable for life. One answer is physical. Earth formed in a region around the sun where liquid water could remain stable on the surface, at least for long periods, and where the planet had the right mixture of mass, atmosphere, chemistry, and geological history. But another answer is observational. If Earth had not been suitable for life, we would not be here asking why it was suitable. This does not replace the physical explanation. It simply reminds us that our point of view is not neutral. We are not random witnesses floating outside reality. We are products of the reality we are trying to understand. The same idea can be expanded from Earth to the universe as a whole. We observe a universe old enough to have stars, galaxies, heavy elements, planets, and biological chemistry. But if the universe were too young for these things, there would be no observers like us inside it. We observe laws of physics that allow atoms and molecules, but if the laws did not allow stable matter, there would be no minds made of matter to notice the failure. We observe a cosmos where structure formed, but if structure could never form, no one would exist within it to call it empty. This is not an explanation in the same way that gravity explains falling or fusion explains starlight. It is more like a filter on what observations are possible. The Anthropic Principle tells us that any universe observed by living beings must have the properties required for living beings to arise. It does not tell us why those properties exist. It does not prove that the universe was designed. It does not prove that many universes exist. It does not solve physics by itself. But it prevents us from treating our location in reality as if it were chosen at random from all possible conditions. This matters because fine-tuning questions can be misleading if we forget the observer. Suppose we discover that a certain feature of the universe lies within a narrow range compatible with life. It is natural to feel astonished. Why is it in that range? Why not somewhere else? The Anthropic Principle replies, gently but firmly, that if it were outside the life-permitting range, no observer like us would be present to measure it. Our existence selects, in a sense, for a universe compatible with our existence. But this answer is both useful and incomplete. It is useful because it explains why we should not be shocked to find some life-friendly conditions around us. A fish should not be surprised to find itself in water rather than in dry sand. A tree should not be surprised to find itself on a planet with soil, sunlight, and air. In the same way, a conscious observer should not be surprised to find itself in a universe where conscious observers are physically possible. This is not arrogance. It is simply a correction for selection bias. Selection bias happens whenever the way we observe something affects what we are able to see. If you only study survivors, you may misunderstand the danger of the journey. If you only hear from planets that produced observers, you may overestimate how ordinary observer-friendly planets are. In cosmology, the selection effect is extreme because failed universes, if such things are physically possible, would have no one inside them reporting failure. Silence cannot send data. The anthropic principle is incomplete because it does not tell us how many alternatives there really are. It speaks most clearly when there is some larger set of possibilities. If many planets exist, then it is not so surprising that observers arise on one with suitable conditions. If many regions of the universe have different environments, observers will naturally appear only in the compatible regions. But when we apply the same reasoning to the fundamental constants of physics, the question becomes harder. Are there actually many possible universes, or many domains with different laws? Or is there only one universe with laws that could not have been otherwise? Science has not settled this. Some ideas in cosmology and theoretical physics allow for a larger landscape of possibilities. Other approaches seek deeper principles, showing that the constants we observe are not arbitrary at all. The anthropic principle can work with the first possibility, because observers would naturally find themselves in one of the rare domains where observation is possible. But if the second possibility is true, then what looks like fine-tuning may eventually be explained by a deeper law. In that case, the universe might not be lucky in the way it appears. It might be necessary. This is why the anthropic principle must be handled carefully. Used well, it is a reminder that observers are part of the system they observe. Used poorly, it can become a way to stop asking questions too early. If someone says, "The universe is this way because otherwise we would not be here," that may be true, but it may not be enough. Science still wants to know whether there is a mechanism, a deeper theory, or a measurable reason behind the conditions we observe. A helpful example comes from the age of the universe. We should expect to live at a time when enough generations of stars have already existed to produce heavy elements, but not so late that all suitable stars have disappeared. This expectation has an anthropic flavor. It connects the time of our existence to the conditions required for our existence. We are not likely to find ourselves in the first moments of the universe before atoms or stars. Nor should we expect to find ourselves in an era where no usable energy sources remain. Our observation of cosmic time is filtered by what life requires. This does not make humanity central in the old sense. The anthropic principle does not say that the universe revolves around us. In fact, it often says the opposite. We are not at the geometric center of creation. We are not the measure of all things. We are a kind of consequence, appearing only where the conditions allow consequences like us. The universe can be vast, ancient, mostly hostile, and still contain rare places where matter becomes aware. Our existence does not make us the center, but it does make our viewpoint selective. There is a quiet humility in this. When we ask why the universe is suitable for life, we must remember that our question comes from within the suitability. We cannot step outside all possible universes and compare them directly. We cannot observe a lifeless universe from the inside if no observers can arise there. We are studying a cosmic sample that already contains at least one success, our own existence. At the same time, this should not drain the mystery away. The Anthropic principle explains why we should not be surprised to observe conditions compatible with life, but it does not erase the deeper wonder that such conditions exist at all. It does not explain why there is a universe, why there are laws, why those laws permit complexity, or why matter can become conscious. It is a lens, not a final answer. In this video, that distinction matters. The universe may not be perfect for life. It may not be made for life. Most of it is empty, cold, and unreachable. But it is compatible with life in at least one place, and perhaps in many places. The Anthropic principle asks us to hold two thoughts together. First, we should be cautious about calling our existence impossible, because only possible observers can observe. Second, we should still feel the weight of the fact that possibility itself is real. So perhaps the question is not only why the universe is so finely arranged. Perhaps it is also why we are able to ask that question from inside the arrangement. We are not outside the cosmic experiment. We are one of its outcomes, made of the same matter, shaped by the same laws, and limited by the same conditions we are trying to understand. As this thought settles, there is no need to force an answer. The universe does not become less beautiful because our viewpoint is selective. It becomes more tender in a way. Out of all the silence, there is this moment of awareness, this quiet breath, this small place where the cosmos is able to notice itself before sleep. Chapter 9. The Multiverse as a Possible Explanation. The multiverse is one of the most fascinating and controversial ideas in modern cosmology because it suggests that the life-friendly features of our universe may not be a single cosmic coincidence, but one outcome among a much larger range of possible realities. At first, the idea sounds like science fiction. We are used to thinking of the universe as everything that exists, all space, all time, all matter, all energy, and every galaxy we could ever hope to see. So when someone says there may be other universes, the phrase can feel almost impossible. Where would they be? What would separate them from us? Could we ever visit them, observe them, or prove they are real? The answer depends on what kind of multiverse is being discussed, and this is where care is important. The word multiverse does not describe one single theory. It is a family of ideas. Some versions come from cosmic inflation, the early period when space may have expanded extremely rapidly. Some come from attempts to understand why the constants of nature have the values they do. Some come from quantum mechanics, where different possible outcomes may all be represented in a deeper mathematical structure. These ideas are not all the same, and they do not all have the same scientific status. For the mystery of a life-permitting universe, the most relevant version is often the cosmological multiverse. In this picture, what we call our universe may be only one region within a much larger cosmic reality. Other regions could be so far away or separated from us so completely that no signal, could ever travel between them and us. They might have formed through processes related to inflation, perhaps as separate bubble-like domains in a larger inflating background. Each region could have its own history, and in some proposals, perhaps even different effective physical constants or different low-energy laws. This idea is not introduced merely to make the universe seem larger. It is introduced because it may help explain why our universe has conditions compatible with life. If there is only one universe, then the values of its constants can feel deeply puzzling. Why should gravity, nuclear physics, cosmic expansion, and dark energy fall into a range that permits galaxies, stars, planets, chemistry, and observers? But if there are many cosmic domains with different conditions, then the puzzle changes. It may be less surprising that at least some domains are compatible with life. Observers would naturally arise only in those rare domains where observation can occur. This connects directly to the anthropic principle. The multiverse gives anthropic reasoning a larger stage. If many different cosmic environments exist, then our presence in a life-friendly one may be similar to finding ourselves on a habitable planet rather than in empty interstellar space. We are not here because every environment is suitable. We are here because unsuitable environments do not produce beings who can ask questions. A useful comparison is the search for planets. Long ago, when only the planets of our own solar system were known in detail, Earth's habitability seemed almost lonely. But once astronomers began finding planets around other stars, Earth could be seen as one example in a much larger population. Most planets may not be Earth-like. Many may be too hot, too cold, too massive, too small, too dry, too gaseous, or too unstable for surface life as we know it. But in a large enough collection, rare worlds are not impossible. They become part of the expected variety. The multiverse applies a similar style of reasoning, but on a much grander and more speculative level. Instead of many planets within one universe, it suggests many cosmic regions within a larger reality. If those regions differ enough, then life-friendly conditions might be rare, but not mysterious in the same way. We would live in one of the rare compatible regions because no other kind could contain us. However, this is where the idea must be handled with scientific honesty. We have strong evidence that our observable universe expanded from a hot, dense early state. We have strong evidence that space is expanding today. We have evidence that something like inflation may help explain the large-scale smoothness, flatness, and tiny early fluctuations of the universe, though the exact nature of inflation remains under study. But the existence of other universes is not directly confirmed. No telescope has shown us another universe. No spacecraft can cross into another cosmic bubble. No experiment has yet provided a decisive observation that proves the multiverse is real. Still, the absence of direct proof does not make the idea meaningless. Some scientific ideas begin as implications of theories developed to explain observable facts. If a theory explains what we can measure and also predicts things beyond direct reach, scientists may take those predictions seriously, but cautiously. The challenge is testability. A scientific idea becomes stronger when it leads to observable consequences that could, at least in principle, support it or challenge it. If other universes are forever beyond any possible observation, then the multiverse becomes difficult to evaluate by the usual standards of science. Some researchers have explored whether signs of other cosmic bubbles could appear in the cosmic microwave background, the ancient light from the early universe. The idea is that if two bubble regions ever touched or influenced each other, the encounter might leave a circular or unusual pattern in that ancient light. This is a difficult search because the early universe already contains natural variations, and scientists must be careful not to mistake statistical noise for evidence of something profound. So far, no widely accepted evidence of such a collision has been found. The sky does contain patterns and small anomalies that scientists study carefully, but none has become a confirmed signature of another universe. Another reason the multiverse appears in scientific discussion is the problem of dark energy. The observed amount of dark energy is very small compared with some theoretical expectations, yet large enough to shape the future expansion of space. In a multiverse picture, different regions might have different values of vacuum energy. Most values might prevent galaxies from forming, but a small subset might allow structure. Observers would then find themselves in one of those rare regions. This is not a complete solution, but it shows why the multiverse is taken seriously by some physicists when discussing fine-tuning. There are also ideas from string theory that suggest an enormous landscape of possible vacuum states, each corresponding to different physical properties. This is highly complex and remains far from direct experimental confirmation. Still, it has influenced the way some scientists think about the constants of nature. If a deeper theory permits many possible realizations of physics, then our universe might be one realized possibility among many. Again, the difficulty is not imagining the idea. The difficulty is connecting it firmly to observation. This is why the multiverse sits in an unusual place. It is not simply fantasy because it arises from real attempts to understand inflation, quantum theory, gravity, and the constants of nature. But it is also not established fact because direct evidence remains lacking. The honest position is neither to dismiss it too quickly nor to treat it as proven. It is a possible explanation, not a completed answer. For a sleep science video, perhaps the most calming way to hold the idea is this: the multiverse does not make our universe less meaningful. Sometimes people imagine that if there are many universes, then our own becomes less special. But science does not measure meaning by uniqueness alone. A forest is not less beautiful because it contains many trees. A star is not less luminous because other stars exist. A life is not less real because other lives are possible. If the multiverse exists, then our universe may be one small region in a reality far greater than we can see. If it does not, then our universe remains the one vast home of everything known. Either way, the mystery remains profound. We still live in a cosmos where matter organized into stars, stars prepared the elements, planets formed from enriched dust, and at least one world became aware of the laws around it. The multiverse may one day become a stronger scientific idea, or it may give way to a deeper explanation we cannot yet imagine. Perhaps future theories will show that the constants of nature had to be this way. Perhaps future observations will reveal subtle traces of a larger cosmic structure. Perhaps the question will remain open for a very long time, standing at the edge of what science can ask. For now, it is enough to let the possibility widen the mind without demanding certainty. Beyond the observable horizon, there may be more space, more galaxies, or perhaps realities with histories entirely unreachable from our own. And here, inside this one visible universe, there is still warmth, breath, and the quiet fact of being present. You do not need to cross into any other cosmos tonight. This one is already vast enough to rest in. Chapter 10. Is the universe perfect or just possible? After traveling through the laws, forces, stars, chemistry, expansion, dark energy, and the possibility of other universes, the final question becomes quieter and more difficult. Is the universe truly perfect for life, or is it simply possible enough for life to appear? The word perfect can be misleading. It suggests a universe arranged with comfort, safety, and purpose in every direction. But the cosmos we observe is not like that. Most of space is empty by human standards. Most places are far too cold, too hot, too irradiated, too unstable, or too starless for life as we know it. Even worlds that orbit stars are usually not gentle homes. Some are scorched by their suns. Some are frozen in darkness. Some are crushed beneath thick atmospheres. Some have no surface at all. Some drift through space without a star to warm them. So the universe is not perfect for life in the simple sense. It is not a garden spread evenly across all of space. It is not built like a comfortable room. It does not protect living things from danger, loss, radiation, impact, extinction, or time. If anything, the universe is mostly indifferent to life. It allows stars to explode, planets to collide, atmospheres to escape, oceans to freeze, and galaxies to drift beyond one another's reach. Life survives only where conditions fall into rare and temporary balance. And yet, that may be the more astonishing fact. The universe does not need to be perfect everywhere in order to be remarkable. It only needs to be possible somewhere. Possibility is a quieter word than perfection, but it may be more scientifically honest. A possible universe for life is one where the laws permit stable matter, where gravity can gather material without destroying every structure too quickly, where stars can shine for long periods, where heavier elements can be made and dispersed, where planets can form, where chemistry can become rich, and where energy can flow through organized systems. Such a universe may still be vast, cold, and mostly lifeless. But if it contains even a few places where these conditions overlap, then life can become part of cosmic history. This distinction matters because it changes the emotional shape of the mystery. If we ask why the universe is perfect, we may be tempted to imagine that everything was arranged around us. But if we ask why the universe is possible for life, the question becomes deeper and humbler. It does not place humanity at the center. It places life within a larger pattern of physical conditions, some known, some still mysterious, all connected. Science shows that life is not made from a separate substance. It is matter following the same laws that govern stars, stones, oceans, and light. A living cell is not outside physics. It is physics organized in an extremely intricate way. It uses chemistry to store information, regulate reactions, build boundaries, and maintain itself away from equilibrium. It borrows energy from its environment and returns waste heat to its surroundings. It persists not by escaping the universe's laws, but by using them. This is one of the most beautiful ideas in modern science. Life is not a violation of the cosmos. It is one of the things the cosmos can do. That does not make life inevitable. The origin of life remains an open scientific question. Researchers study how simple molecules may have formed more complex networks, how information-bearing chemistry could have begun, how membranes may have enclosed early systems, and how energy gradients could have driven self-sustaining reactions. There are promising ideas, but no complete final story. Earth tells us that life can emerge under planetary conditions because it happened here. but we do not yet know how often it happens elsewhere, or how difficult the transition from chemistry to biology really is. This uncertainty keeps the final question open. If life is common, then the universe may be broadly fertile, not perfect, but generous in its opportunities. If life is rare, then Earth may represent a fragile and unusual success, one small island of awareness in a mostly silent cosmos. If intelligent life is rare even where simple life is common, then consciousness may be an especially delicate outcome. At present, science cannot honestly choose among these possibilities with confidence. What we can say is that the universe permits complexity. That alone is profound. From an early hot and simple state, it evolved into a cosmos with structure at many scales. Particles, atoms, molecules, dust grains, planets, stars, galaxies, clusters, and living systems. Complexity did not appear all at once. It grew through stages, each made possible by earlier stages. The universe cooled, matter organized, stars enriched space, planets assembled, chemistry diversified, and at least once, chemistry became aware. But complexity always depends on conditions. It needs stability, but not complete stillness. It needs energy, but not uncontrolled violence. It needs change, but not chaos so extreme that patterns cannot last. A living world is balanced between order and motion. Too little energy and chemistry becomes frozen. Too much energy and delicate structures are destroyed. Too little change and evolution has little to work with. Too much change and life may not survive long enough to adapt. In this way, life belongs to the middle. It appears not in the most extreme conditions, but in places where forces, temperatures, materials, and timescales become compatible. This does not mean the universe was designed as a perfect home. It means that among its enormous range of environments, some are moderate enough and rich enough for life to explore. The same may be true of meaning. Science does not tell us that the universe has a purpose in a human sense. It does not show that stars exist for us, or that galaxies were arranged so that life would appear. But science also does not make the universe meaningless. Meaning is not something a telescope can measure in the same way it measures light. Meaning emerges in minds, relationships, memory, care, curiosity, and experience. If the universe permits minds, then it permits meaning to arise within itself. This is why the phrase, "the universe shouldn't be this perfect for life," is so powerful. It expresses a real sense of wonder, but the conclusion does not need to be literal perfection. The deeper truth may be that the universe is not perfect at all. It is severe, vast, unfinished, and mostly beyond us. But it is possible. It is possible enough for stars to make carbon, possible enough for water to remain liquid on at least one surface, possible enough for cells to evolve, possible enough for nervous systems to form memories, possible enough for a listener late in the day to close their eyes and think about the laws that made thinking possible. That may be more moving than perfection. A perfect universe might feel fixed and obvious. A possible universe feels fragile. It carries uncertainty. It could have been otherwise, or perhaps it could not have been otherwise, and we simply do not yet understand why. Either way, our existence becomes a question, not an answer. We are not proof that everything was arranged for us. We are evidence that matter, under the right conditions, can become aware of being matter. It also reminds us that scientific humility is not the same as emptiness. When scientists say they do not yet know why the deepest conditions are this way, they are not saying the question has no answer. They are saying the answer has not yet been earned. The history of science is full of mysteries that once seemed unreachable, then slowly became clearer through measurement, mathematics, and patient doubt. The fine-tuning question may follow that path, or it may remain partly beyond the methods we have now. Either way, the mystery is real enough to study and wide enough to inspire. The final lesson is not to solve the mystery too quickly. Fine-tuning may one day be explained by deeper physical laws. It may be connected to a wider multiverse. It may be partly understood through selection effects, because observers can appear only where observation is possible. It may also reveal gaps in our current theories of space, time, energy, and matter. The honest scientific position is to remain open, careful, and curious. But curiosity does not weaken wonder, it deepens it. Every unanswered question becomes a doorway rather than a wall. Why are the laws this way? Why do constants have the values they do? Why does the universe contain stable matter? Why does chemistry become complex? Why did life begin here? Why is there something that can ask why? Perhaps the universe is not perfect. Perhaps perfection was never the right word. Perhaps the better word is permitted. Reality permits stars. It permits planets. It permits oceans. It permits chemistry. It permits life. And in this small moment of cosmic history, it permits awareness. As this journey closes, let that awareness become gentle. You do not need to decide tonight whether the universe is lucky, necessary, rare, or one of many. You are here inside the possible, held by laws older than Earth and warmed by a star that rose because the cosmos allowed it. Let the question remain open, soft and spacious, while the day fades behind you and the quiet universe continues on. And so, my friend, the universe may not be perfect for life in the simple sense. It is vast, cold, ancient, and mostly beyond us. But it is possible enough for life to appear, possible enough for matter to become aware, and possible enough for this quiet moment to exist. If you're still awake, you can continue the journey with another video and let the next mystery carry you a little farther into the night. But for now, let the questions soften. Let the day fall away. Rest well, my friend, and sweet dreams among the stars.